As observations, say from Hay et al., that I'm showing here, show they have a range of different properties, be it a range of masses, sizes, velocity dispersions, surface densities, etc. So that means that we actually have a range of different star-forming environments. And we need to understand all of these if we're really going to get a handle on star formation. And then to just make things even simpler, stars like to influence their environment through feedback and other processes. So that changes the GMCs, and of course, then changes the environment in which stars form. As I said, I'm going to be talking about efficiency of star formation. So I'm going to throw up the definition I'm going to be using throughout this talk. There are other definitions, but this is the one that I'm going to be using for today. We have the mass in young stars on the top here, the free-fall time of the gas, the maximum age that we consider a star to be when it's still young. So in this case, this is going to be 4 megayears. And then we have the gas mass of the GMC. And this is an observational quantity. It's been observed several times, lots of times. And here's kind of a summary of some of those observations. You can see a lot of them are for the Milky Way. There's a large scatter, and then each of them have a kind of a median value as well. So this is a more recent Milky Way value. And you can see, although resolution of the observations affect the scatter, overall, the scatter remains independently. And it's this scatter that really piqued my interest a couple of years ago when we started this project. And to study that, we're using a numerical simulation. It's a Milky Way-like galaxy run from the Agora initial conditions. We have a spatial resolution of 4.5 parsecs, and each star particle that forms, which you can see over here, it has a resolution of about 300 solar masses. We have a feedback model in there as well, which is the Agora 2013-2015 feedback model, which has a few different components, so radiation winds, radiation pressure, and supernovae. So in order to model the properties of GMCs, we actually need to identify them in the simulation. So if we take the surface density map here, we decided to make 2 different ways of identifying GMCs. First one, which we call 2D, is where we take a surface density map of the molecular gas in the simulation. Then we apply a clump finding algorithm and identify the GMCs that way. And the second method, which we're calling 3D, is where we actually use a built-in clump finder inside Ramses and identify GMCs using the full information that we have there with a 3D volume rather than a 2D surface. But just to convince you that GMCs exist in the simulation, if I zoom in quickly, and then I can show you some of the GMCs. This is found with the 2D method. I'll zoom in one last time and also overlay the molecular map that we use, which is the gray 2D map there. So if I kind of bring back Hayer's data and now overlay GMCs from the 2D clump finding method, you can see we actually get a pretty good match. In all properties, we are limited by resolution at the low mass end and the small radius end, but overall we do pretty well. In 3D, we find that we have a shift in properties to larger values, mostly just because objects that are in projection appear as a GMC. When you're actually measuring them in 3D are not connected, and so fall below our criteria. You can combine these, of course, into the Larson relations, which I'll show here. So the black contour shows observational the Hayer data, and then the colored histogram in the background there is our simulation. So you can see we're matching pretty well. So from this work, we're pretty confident that our GMCs are analogous to those in the real Milky Way. So if I bring up some observational data for efficiency, this is from Lee et al., 2016. We have efficiency here and the total mass of the GMC on the y-axis, on the x-axis, sorry. You can see there's a negative trend, but we can also use this to determine a histogram of the efficiencies, which is shown here. There's a median here of about 1.8%, which is kind of what we see universally. If I throw on the 2D data, you can see we match the distribution well in both panels. We get a median that's pretty close to about 2.6%, so within a factor of 2. And in 3D, things change a little bit, but we're still doing reasonably well in that we're now squashed the distribution, and our median value of efficiency has dropped to about 0.8%. But overall, all three are consistent with about 1%. So to convince you that this is not purely a result of what we put into the simulation. This is the star formation law that the simulation uses. So we have some fixed efficiency that every cell in the simulation forms stars at, and then we multiply that by the mass of that, the molecular gas mass in that cell divided by the free-fall time of that cell, and we get a star formation rate. Now, the efficiency that we put in, it's fixed for every cell throughout the entire simulation run, is at 10%. And what's interesting about this is it's not recovered in the GMC data. Now, of course, when we're calculating it for the GMCs, we're averaging over large volumes. We're not dealing in individual cells. So it doesn't seem to be that important at first. But if we think about this in terms of observations, what this really means is that until we get observations that are smaller than the scale of GMCs, we're not going to be able to determine if there is some universal star formation efficiency that everything forms at. But to go back to the scatter and try and explain it, in their paper, Lietow presented a toy model, which is described by these four equations. Basically have an amount of gas lost as a function of time, amount added as stars, fixed free-fall time, and then some efficiency that goes as the age of the cloud. And you can plot this nicely for different efficiencies as a function of age. So the solid line is independent of the age of the cloud, where the efficiency scales linearly with the age of the cloud, and then where it's to the age of the cloud squared. Now, this model assumes that all GMCs follow the same evolutionary path, and in order to get the scatter, you therefore have to observe the population of GMCs at a range of different ages. So that gives you a scatter like this. So the purple is the model scatter, the gray points are observations, and as you can see, it's when the efficiency is approximately proportional to the age of the GMC squared is when the model fits observations best. How did the simulations do? So to start off with, here are 6 randomly selected GMCs from the 3D clump finder. You can see there each GMC has a unique path in these parameter spaces. So sorry, I should have said this is gas mass, total stellar mass, young stellar mass, and the efficiency is a function of time, the measured efficiency. So you can see each GMC has a unique path, but that's just 6. We've got thousands, so I'll put up all of them in this histogram here. And you can see that really, although we have similar trends, we tend to decrease as age, say in gas mass, we're not actually matching this model very well at all. In fact, we're finding that each GMC has its own path in these parameter spaces, and as a result, a wide variety of values. So the next thing we looked at was actually individual properties of the GMCs and how they correlate to the efficiency. So if we start, say, with the free-fall time as a function of the efficiency as a function of free-fall time, you would kind of expect there to be a relationship there as we use the free-fall time in our definition. But what about other properties? So we can have gas mass, distance from the galactic center, velocity dispersion, size of the GMC, density of the GMC, viral parameter of the GMC. And although we are finding correlations here, so density, which we might expect, there isn't one property that is really driving a strong sense of the scatter in the efficiency. There's not one thing driving that. And just to kind of show that it's not even, to think about how the clouds evolve in this space, we can put up our tracks on there. As you can see, they can be a little bit muddled. I'll zoom in on the gas mass one. And again, you see each GMC is following a unique path here. There isn't one way that the GMCs are evolving. And with that, I'll come to my summary slide. So thank you very much.
Thank you, Kearn.
There have been claims that the efficiency is related to the boundness of a cloud. Did you look at that?
So that would come into, I guess, the virial parameter of the cloud, which, if I just go back, I mean, obviously we have a correlation here, but it's not super tight. I mean, we have most GMCs sit down here, and then we have this kind of branching off of it. So, although I think obviously it plays a factor. High efficiency ones, high efficiency GMCs are in the high virial parameter. So I've forgotten which way around it is. But yes, there is an impact there, but I don't think it's the key one.
So, Kearn, can you tell us anything about the total lifetime of the GMCs?
So in our simulation, we find a variety of lifetimes. Most lifetimes are of the order between 5 and 10 mega years. And I know the Lee model is based on assuming 20 mega year lifetime. So that does change how that model works. We've actually looked at shifting the model, and it's possible, but instead of, if we go back to that model, sorry, 1 second. Instead of having most GMCs kind of end up at approximately the same age, you end up with a larger scatter at when they effectively die by trying to give it, in this particular model. We haven't looked at other models yet. So it could just be model dependent in that case. That will change how we compare with these.
Okay, thanks. Alberto, can you please come sit up?
So you showed very nicely that the GMC bulk properties look a lot like observed GMCs, but the resolution of the simulations are still limited on the scale of the internal structure of the GMC.
Sure.
So, but what would be nice or interesting is if you used the GMCs in your simulations as kind of the large-scale initial conditions for resolved simulations of the evolution of individual GMCs. Have you thought about doing that because of the large-scale driving of the turbulence, the inflow of gas? These things are hard to capture in small-scale turbulence simulations.
So at the moment, we haven't planned to do that. The next stage we're looking at is actually different star formation prescriptions instead, and keeping the resolution the same. We have kind of realized we have this limitation, and that's why, for the most part, we're kind of talking about the bulk properties. But I think you're right. I know there is some work on trying to model those internal properties from large-scale simulations, cutting those out. We're not there yet for this simulation.